Maybe you should try. I see, Paul, you are laughing.
I think it might be an issue just because of background noise. When it quietens down, it should be
Okay.
What I'm going to do is bring the lights
Okay.
down.
Okay. So, thank you very much. Welcome to this Sentinel-1 session. It's my pleasure to be here with you today. I think that it's a long time that we haven't met together in this community, so it's really a pleasure to be here. I am Nuno Miranda. I'm the Sentinel-1 mission manager. It's a pleasure to share or co-share this session with my colleague Muriel Pignon, which is the data quality manager. This session will have 4 presentations. The first 2 presentations will be given by myself and by Muriel, where we will basically give a broad overview of where we stand with the missions. Muriel, I'll let you introduce the 2 others presentation if you want.
Yes, so following this overview from Nuno and myself, we are going to have 2 presentations that are coming from the Mission Performance Center, which are giving more details in some relevant parameters that we monitor, which are related to INSAR, and then also in a recent development that we had in our processor, which is related to RFI, and also the impact that it might have in interferometry.
So I think that we're going to start with the first speaker, which is me. Can you hear me okay? Yes? Okay, perfect. Is it hard to understand? Okay. So, I need this one, yes. So, so in this presentation, I'll try to give you a broad overview of the Sentinel-1 mission, what we have done over the last years and where we are heading to. I'd like, before starting, to acknowledge all the co-authors of this presentation that helped me in putting together all these slides. Is it okay if the volume is fine? Closer? Okay. Before diving straight away into Sentinel-1, I'd like to start this presentation by widening a bit the landscape and presenting briefly what are the ESA observation programs. That is basically composed by 3 different pillars or elements. The first one is the science elements, which is articulated around our Earth Explorer missions that are really state-of-the-art instruments that are there to consolidate science around climate variables or biogeophysical variables. In this science family, you have in particular 2 satellites, which are biomass, which is the first P-band space-bound SAR quad-pole that will be flying, as our director was saying, around 2025. And we have the Harmony mission, which will be the first companion mission to the Sentinel-1 mission. Those 2 satellites that will fly, Harmony will fly around together with Sentinel-1D towards the end of this decade. Those 2 missions will be presented tomorrow by my colleague Björn Norman and Paco Lopez-Decker. The second pillar of the ESA Earth observation program is the Copernicus program. Basically, Copernicus aims at providing operational missions which targets the development of operational applications and operational services, and basically support the implementation of the European policy. It's in this program that we have our flagship spacecraft, the Sentinels, Sentinel-1, Sentinel-2, but also those missions that are now complemented by a new program that is less known, which is the Copernicus contribution missions. And that will be soon complemented by what we call the Copernicus expansions, like the Roselle mission, which is the L-band SAR from Europe, and also the Sentinel-1 next generation that will be, the 2 of them that will be presented by Malcolm tomorrow. Finally, the last component is the Meteo component, where ESA develops the satellites, and those are operated by EUMETSAT, our sister agency. The previous slide was talking about the future, but it's always good to step back a bit and to recall where we come from. Sentinel-1, I used to say, is standing on the shoulder of our precursors like the ERS mission, the ENVSAT mission, and also on the shoulders of the Canadian RadarSat Constellation mission. I think that those missions have been necessary to develop most, if not all, the applications that today Sentinel-1 and RCM are today supporting, and that have been key to develop the European leadership in SAR and remote sensing in particular. Overall, if you look back, it means that we have now 30 years of data record at C-band that are extremely useful to look at climate data records or science in general. This slide is a bit busy, and I think that a lot of people was a bit expecting this slide. It gives it presents the agenda of the Sentinel-1 mission. It's busy, and the mission is really, I used to say, running in a complex context. The mission started in 2014, as has been recalled by Joseph, with the launch of Sentinel-1A from a Soyuz launcher in Kourou, and that has been complemented 2 years after by Sentinel-1B. And the mission was running nominally up to the premature failure of Sentinel-1B back in December 2021. So we are now running in what I call a degraded configuration, and it puts a lot of pressure, as I used to say, in the remaining unit that is Sentinel-1A. Sentinel-1 was running nominally. I've been performing nominally over the last years up to October last year, where we had a major failure on the propulsion system that forces us to switch to the redundant side, putting even more pressure into the system. All in all, it makes that it is the ESA and the European Commission top priority to launch Sentinel-1C as soon as possible. Today, we don't have a clear date for the launch of Sentinel-1C. The launch was supposed to be in May this year. That has been postponed to December after the failure of Vega C back in December last year. And that has been postponed another time towards, we hope, spring to autumn next year due to the negative outcome of the engine test that happened before the summer. So we are actually looking for a very successful 2024 year because we hope that at this moment we will successfully dispose the Sentinel-1B spacecraft. We'll see that later. I have a slide on that, on the fact that we are currently doing the disposal of the spacecraft. Sentinel-1 will reach 10 years in space. I think that's something that we need to celebrate, but it changed the way we used to do SAR and to use application of SAR worldwide. And we are looking forward to have a very successful launch of Sentinel-1C. This slide is another slide that is a bit busy, but that presents the Sentinel mission in a nutshell. The mission is a constellation of two satellites located in the same orbital plane, 180 degrees apart, in a near-polar sun-synchronous orbits at around 700 kilometers. We have both spacecraft, or each unit have a 7 years lifetime, with 12 years for consumables, which means that 12 years of fuel, basically. We have a 12 days repeat cycle interferometric-wise for each satellite, 6 days if we consider the mission. The main payload is, of course, a C-band SAR at C-band, yes, with single and dual pole capacity, incidence angles from 20 to 45 degrees, and a very stringent radiometric accuracy requirement of 1 dB 3 sigma, and fairly okay noise equivalent sigma 0 of -22 dB. Sentinel-1C will provide another payload for the first time, which is NIS. In terms of imaging modes, I think that you all know them pretty well now. We have 4 exclusive imaging modes. The strip map mode, which is a legacy mode. Actually, I think that strip map will be abandoned for Roselle and for Sentinel-1 Next Gen. So it's the last time maybe with Sentinel-1 first generation that will fly this mode. We have our main horses over land masses, which is the interferometric wide swath that relies on the TOPS mode. IWS has a swath of 250 kilometers and a resolution of 5 by 20 meters. Is little brother, which is the extra wide swath mode, mainly used over polar areas, with a swath of 400 kilometers and a resolution of 5 by 20 by 40 meters. Everywhere over ocean, the default mode is a wave mode that is operated everywhere where we don't have any of the 3 other modes, basically. In terms of programmatics, Sentinel-1C and D, they are ready. There are no developments anymore. Both of them are in storage, and we are just launching just waiting for a launcher now. Operationally, operation-wise, the mission is really characterized by systematic data acquisition, systematic data processing, with a predefined user observation scenario. I remember in the previous FRINGE or previous Living Planet symposiums, the users were asking us to be as boring as possible in terms of observation scenario, and I believe that we succeed on that. The instrument duty cycle is quite huge, 25 minutes. Initially, at the beginning of the mission, it was 25 minutes over a sliding window of 100 minutes. And this, we'll see that later, this constraint has been relaxed to 30 minutes outside the eclipse. And we can operate in wave mode for all the rest of the orbit. I think that one of the key characteristics also of the mission, and it's the key to its success, is the fact that the data for the first time is full, free, open, and easily accessible. I believe that I will skip this slide because you know everything about it. Okay, so these slides basically presents the systematic Sentinel-1 observation scenario that we are putting in place in several years. In the left-hand side, you see the scenario that we have been running since more or less the launch of Sentinel-1B that represents the configuration with 2 satellites flying. On the right-hand side, you see the situation or the observation scenario that we are playing now in this, let's say, degraded or contingency scenario with Sentinel-1 only. You can immediately see what is the impact of losing one satellite, which is that basically we lost our capacity to do global coverage. And of course, we have to make some choice and trade-offs, and we kept the priority to support European users, European services, and also to keep imaging over major area of interest like tectonic areas or volcanoes. We also have lost, as you can see, is the pointer working? Yes, we also have lost our capacity to do 6 days a repeat cycle, and we have a much degraded revisit over northern areas. All this information is available online. There is nothing new. But I wanted to spend a bit more time on what we are doing now. It's not the first time that we are running a scenario of 1 satellite only. We are doing that, of course, before the launch of S1B. And these slides try to show you what are the differences of the observation scenario before the launch of S1B and after the failure of S1B. And in this plot, basically, you can see on the right-hand side that the logic of the contingency scenario on which we are running now is really meant to disrupt as less possible the time series worldwide. So you can see that if you look at specific areas that I have highlighted here, we have a much better coverage with 1 satellite over North America, over European waters, over Africa, over Asia, India, Australia, Indonesia. So that's really the logic of the scenario that we are running now. And of course, this has a counterpart. And the counterpart is that you can see that over northern areas, we are doing much less than what we were doing before. And this is possible thanks to the cooperation that we have with CSA and the RADARSAT constellation mission that have been we have been working with them in order to put in place some contingency measures. So RCM is acquiring much more of this data for supporting our Copernicus services, and in particular the marine service for the CIS, services. So this is really important. It's really trying to make you understand that we are today making a huge effort in order to make sure that worldwide, not only over Europe, but worldwide, the time series is kept at least at 12 days. This slide basically shows the average GT cycle, I think, per day for IW and extra-wide all combined. I think that it's important to mention that the improvement that we had in coverage that we have seen in previous slides, we are doing much more over certain areas, is a direct consequence of the duty cycle optimization that we have done over the years. And this came in several steps. Of course, first, at the beginning of the mission, we slightly ramp up the observation in order to put the system space and ground into stress. At some point during the mission, back in, I think it was in 2007, we introduced EDRS, which is the European Data Relay Satellite that offers us more capacity of acquisition and more capacity of downlink. And you can see how by introducing EDRS, we have been able to increase significantly the duty cycle. The other optimization that we have made back in 2018, I think, yes, was the relaxation of one of the main constraints that we're having in the instrument, which is this maximum 25 minutes of a duty cycle that have been relaxed, and now we can operate up to 30 minutes outside the eclipse. You can see here it's a very short period between May to August, where we are constrained to 25 minutes, and outside this period we can go up to 30 minutes. You can see also that, so we have been trying to optimize the duty cycle over the time, but now we are reaching a cap. I mean, it's clear that we have no more capacity with Sentinel 1A. We try to accommodate for some user requests here and there, but there is no capacity left in order to increase the sensing substantially in specific areas. Just to give a bit to open a bit the box of this slide. So this slide basically gives the amount of high bitrate data that we are acquiring today, and it separates now this time by IW and NW. And the previous slide was hiding a reality that is with the increment that we had of duty cycle over the years. We favor much more IW, and we favor much more the acquisition over land masses and the construction of INSAR time series than acquiring data over northern areas with extra wide swath. All in all the optimization that we made and the logic that we had in our observation scenario makes us that Sentinel-1 is, even if we are running in the degraded configuration with one satellite, is really prompt in supporting cryosine, in providing archive, and in providing fresh information to support extreme events like earthquakes. You have here few examples, but there can be plenty of them, of the earthquakes that happened this year over Turkey. We are also supporting the forecast of hurricanes. This is the example of Hillary that badly hit California this August. This data, complementary to RADARSAT 2 and to RCM, are really helping the Met offices in tuning or verifying the accuracy of their provision, and also for supporting events like flood. In terms of processing scenario, nothing had changed here. I think that there have been no change with respect to the previous years. All IW data is processed systematically to GRD and to SLC. and is available, I think, few hours after the sensing. The data is distributed to you with timeliness of maximum of 24 hours, but I think that, if I remember well the numbers, all the data is available a few hours after the sensing. So IW global processing in SLC, and there are, we also process some extra wide SLC marginally. Actually, I just discovered recently that this area has been increased in terms of processing for SLC. I don't know the reason why, or none of my colleagues are capable of explaining why. So if there is someone that is using this data here, I would like to speak to him, actually. I think that in terms of data access, the mission is a great success. I think it's very good that we acquire a lot of data systematically and making it available. It's another thing to have this data actually used by the users. And the data access is something that we are carefully looking at and that we measure through indicators that are measured regularly over time. One of them, one of the major one, is basically the number of users. I think that in terms of number of registered users, we reach something like 500,000 of registered users. That can be my grandmother and so on. But what's really important is the number of active users. You can see that the number of active users, which is people that is actually accessing, downloading the data, have been increasing linearly over time. And it seems that this trend just doesn't stop. For Sentinel-1, we have now more than 20,000 active users. We are generating a huge amount of data per day. And what another criteria that is extremely important in terms of data access is what we call the archive exploitation ratio, which is basically the number of times the archive have been downloaded. And for Sentinel-1, we are reaching, depending on how you look at the data, how you look at the numbers, between 20 and 12 and 20 times the archive have been already downloaded. So I think this is a great success. How long do I have, Muriel? 5 minutes? Okay, I'll try to speed up a bit. Over the last years, the Sentinel-1 ground segment underwent a major transformation to cope with new challenges. So we need to be ready in order to cope with the huge increase of data volume that will happen with Roselle, for example, but more pragmatically also to cope with budget reductions that we're also having. This transition has been made in a transparent manner to you. It has been made over the time, and I think that over the last 2 or 3 years, you haven't marginally seen any disruption on the service that we are providing to you. We are now entering the last mile, and I think that this last mile won't be transparent to you because we are in the process of totally changing our data access system. For a decade, the data has been distributed through what we call the Sci-Hub or the Open Hub, and this system will be discontinued now, and I think that it will be terminated in September or October this year. It will be replaced by a brand new system that is already available, that is already in place. And that is gradually ramping up according to a roadmap that we have been published over the years. What is important is that this data access will offer brand new services or new services that we were not offering before. I think that it's important to mention that all the level 1 data of Sentinel-1 is back online. Over the last years, we received a lot of complaints from you mentioning that it was super difficult to get to access archive data because the data was not online anymore. And I think that now the data is back online. In addition, we'll have new APIs in order to access the data. We still have the OpenSearch and the Open Data APIs, but those will be are there for legacy reason, and they will be complemented by more advanced API like Stack API, and you'll provide basically also direct access to the S3 bucket where the data is. We'll offer also to you capacity for on-demand processing with some limited credit. That will allow you to reprocess, I don't know, a certain time series of IW or to process some extra wide data to SLC if the time series doesn't exist. We'll also offer additional data sets. So this is not only a data access for Sentinel-1, it's an integrated system that provides Sentinel-1, Sentinel-2, Sentinel-3, but also other data sets like the Copernicus DM and so on. And we'll also offer native cloud services, allowing for the people willing to plug its own application in its own software close to the data, that will be made possible. I need to speed up a bit. This is just to present you the approach that we are doing for the disposal of Sentinel-1B. So we lose Sentinel-1B back in December 2021, and the spacecraft entered into disposal phase in August 2022 when we started preparing basically the disposal. The disposal that we put in place is a phase approach where the objective is mainly twofold, is to deorbit the satellite in 25 years and fully dispose the spacecraft, having depleting completely the fuel. So this phase approach have started already. We started by lowering the spacecraft by 2 kilometers in order to clear the orbit for the new satellites like Roselle, Sentinel-1C, Sentinel-1D. In order to do the massive deorbiting, we are using a new attitude that has never been used so far. So we had to enter for a period of 2 months of testing this attitude, and we are now in the period where we are massively deorbiting or lowering the orbit. We hope that our disposal orbit will be below the Starlink envelope, so at an orbit around 530 kilometers, where we'll start to do some depletion burns in order to entirely empty the tank. At that moment, we will passivate the spacecraft. The spacecraft won't be a space debris, but a well-known space object, well-tracked space object. And if everything goes okay, we'll have a natural decay of, it will re-enter the atmosphere in 12 years, much better than the 25 years guideline that we have. So where are we? So far, so good. We are massively lowering it. During the summer break, we paused a bit the activity because of some problem of the thrusters that we are currently fixing. And this will restart it soon, and I think that we are looking for a full disposal towards February and March next year. Just a recall, ERS-2 is still flying and will finally enter the atmosphere this year. So last slide. I need to be quick. I have 3 slides more on Sentinel-1C. So this is just to give you a status of Sentinel-1C and D. The role or the goal of 1C and 1D is to continue the 1A and 1B mission, of course. It flies exactly the same SAR, so there won't be any disruption in terms of SAR mode, characteristics, and so on. Sentinel-1C is built, 1C and 1D design is built on the same design as 1B with evolution, some improvements. The main improvement or the main evolution is that we have this AIS payload. We have also changed the internal calibration scheme that would allow us to marginally improve the radiometric performances. We have qualified the spacecraft for launching with Vega-C, and previously it was Soyuz. And 1C and 1D are ready for launch. So this is just to show you a bit what we expect to have in terms of improvements of radiometric performance. Those are marginal improvements. We basically changed the internal calibration approach that will allow us to achieve a slight better radiometric stability. But I think it will be very hard to see that any improvement if we compare that to the noise that we have in the time series over the transponders, but still. And I think that the most important is that the change of the internal calibration approach allows us to introduce proper noise pulses all along the data take. And thanks to that, we'll be able to perform a much better denoising that we are doing today with 1A and 1B. And this is my last slide. I think the last thing that I wanted to mention was the fact that we'll introduce this AIS, which the scope, of course, is to provide a mean to improve the ship detection and ship identification. The AIS will be run in parallel of the SAR data. The footprint of the AIS has been made such that it matches the IWS footprint in order to maximize the SNR and to minimize the problem, the message collisions. The IAPS observation scenario is still under discussion. Likely, we'll go for a real-time scenario over European waters. This is a clear scenario that has a clear interest for our Copernicus services. Elsewhere, it's still to be defined, so I would be happy to discuss with you some of possible scenarios. And the data policy for the AS is still not yet defined, and we are discussing that with the Commission. Thank you very much. I think that at the end of the session, we'll have 10, 15 minutes for questions. So I'll introduce my next speaker, which is Muriel Pinheiro, which is the Sentinel-1 Data Quality Manager. She's basically taking care of the performance of the Sentinel-1 mission, and she'll give us a status of where we are.
Do you have a pointer? Or the slide changing thingy? The slide to change the slide? Hi. So good morning, all. I'm going to be talking about the product's performance of Sentinel-1 today. So I start here with a brief overview. So first I'm going to speak a little bit about the mission performance cluster, and then give some highlights on the instrument and data performance, move on to some products and evolutions that we have had recently, and then finally highlight some of our ongoing activities, giving some focus to things which are related also with the recommendations of the last FRINGE, which can be found in the conference website. So starting with the mission performance cluster, following the CalVal approach that we have for Copernicus, when we enter operations phase 2, the CalVal is carried out by what we call the SAR-MPC, the Mission Performance Cluster. So this is a consortium formed by different experts from different European companies and institutions, and it is responsible for several things, including, for example, user iteration, the routine quality control, the expert data analysis and monitoring, the CalVal, the execution of the CalVal approach, and also the provision of the reference data that we typically use for our approach, the maintenance and evolution of our algorithms, both for the level 1 and level 2 part, and the monitoring of the instrument. I give you some links so you can have some further information, in particular in terms of the algorithms and in our processor versions. You can find in the SAR-MPC website a complete list of the evolution of the processor, including the latest version and the upcoming one, which should be deployed in the next weeks. You can also find in our online library several documents, including our activities and our product specification documents. The MPC, in its CalVal monitoring, it's also responsible to issue some documentations. We compile the performance information. In particular, I bring your attention to the annual performance report, which usually appears around February, March. And here you have a link to the 2022 one, where you can find an extensive compilation of results spanning from level 1 and level 2, showing that the performance of our main quality indicators is stable. And we also have a series of quality disclaimers that disclaim problems, anomalies that we might have in our data sets. In particular, these quality disclaimers can be for things which are a single event. For example, in the case where we have some data which is processed without external orbit information, and I leave here some examples. And we also have some quality disclaimers for problems which are repeatedly occurring in the data. In particular, right now, we have monthly reports tracing RFI residues, a known problem that we currently have with our burst ID, which should be solved now in the next weeks with the deployment of the IPF 3.7. And also some issues which are related not really with the level 1 data, but more with the external information which we use, in particular the pod near real-time orbits, which currently have a slight degradation due to the increased solar activity. I take the chance to point out to the presentation or the poster from our pod colleagues that should give you all information about our pod orbits. So I just want to encourage all of you to always contact us when you have issues related to data quality that might be useful to you, because we are prepared to perform expert analysis to help sort out what is happening, but it's also very helpful to us because it helps us to improve our approach and improve our data continuously. So I go now for some highlights on instrument performance. We monitor several parameters, and you can find a full analysis in the annual report that I mentioned before. Here I put some example of the monitoring of the antennas. So we compare the current status of our TRMs with reference status in the beginning of the mission, and this allows us to see if we have failures or degradations in the quality of the TRMs. Nothing noticeable has been seen in the last years. So there is a minor event happening in one particular TRM that I emphasize in the circle. It has a slight drop in gain for the H polarization. We monitor this particular TRMs closely, but nothing has been noticed in the last couple of years, and the quality of the data is preserved. We also monitor the instrument noise. Here we do typical analysis using our level 0N engineering data, and we check the noise for different subswats, and also we separate between land and ocean because we know we have different contributions from these different targets. And what you can see here is that the instrument noise is very stable. You see in the table comparisons for the latest results with the previous years, and everything is stable. We also monitor some parameters concerning interferometry, in particular the burst synchronization in the baselines. I'm not going to say anything about this because the next presentation is entirely focused on the topic. And we also monitor the radiometry. Nuno has already showed this plot, but here basically we have a time series that spans from 2017 until today for Sentinel-1A and until the failure of Sentinel-1B. And as you can see, the radiometry is relatively stable and we are within the performances. One thing to notice is that we continuously improve the quality of the radiometry, and that includes sometimes adjusting the calibration factor, and in particular also adjusting our elevation antenna pattern, hopefully to improve the quality of the data. And this sometimes makes that our data, our time series has some slight discontinuity in the radiometry. This is mostly seen here in the time series of Sentinel-1B in this vertical line. So what we did also recently was to document an approach to post-process this discontinuity and correct it using a recompensation of the antenna pattern. So here you can see the consistent time series, and then you note that everything is a little bit more homogeneous, and the performance is also slightly improved. I leave here the link to the paper where we describe the approach. We also try to improve our Calval approach as we go. In particular, recently we have been trying to tackle an issue that is known, which is a slight worse calibration that we have for the HH polarization, and also some inconsistency in the behavior that we have across the modes for this polarization. So in order to try to tackle that, we have recently changed a little bit the mission acquisition over some specific targets, in particular over the Canadian transponders, also in comparison with CSA for the activation of their transponders for Sentinel-1. We have also now alternating HH and VV acquisitions, both for the CSA site and also over Surat. We have also increased a little bit the pattern of acquisition of our rainforest targets to have some overlap EW and IW acquisitions with similar geometries. And we are now analyzing all the data to see if we can improve a little bit the HH radiometric calibration as well. Here you can see some gamma profiles, which are these profiles over the rainforest that we typically do. And you can see here that we did confirm that we have a slight offset between IW and EW. So we plan to do a calibration of EW relative gains. We also monitor the absolute location error. In particular, we do two kinds of analysis. First is what we call out of the box, which means we don't apply any atmospheric correction, any solid earth And this is the results that we get. You can see that even though we don't apply any of these no corrections, we still have a relatively good geometric accuracy, definitely still within the requirements of Sentinel-1. And of course, once we go for the more precise characterization of this error, then including all this environment and system corrections, then we are able to reach a decimeter accuracy. We have also run recently a recalibration of the timing offsets that we have. So these are these global timing offsets that are required to center this cloud of points that I shown just in the previous slides. This has been done in the context of our new product, ETAD, that I'm going to talk about a little bit later. So basically, this product has an auxiliary data, which is called AUX-ITC. This is available in the SAR-MPC website, and this auxiliary data has annotated these calibration offsets that one would need in order to achieve this zero bias geometric calibration. So we have, in the last months, run an extensive recalibration of these offsets and profiting from different calibration sites, in particular Surat, plus data from the geodetic observatories. And with the results, we can see that the biases of Sentinel-1A and B, especially in range, are now closer to zero. We have also been trying to see if we can put some corrections to compensate some offsets that we see in the subswat. So if you go back to the previous plot, you can see that in particular the calibration of the IW1 seems to be a bit off in the Surat data analysis. But this is ongoing, and at the moment we do not see a lot of consistency in the results of the different sites, so this is under investigation. This auxiliary data, which is available in the website, is prepared to contain some offsets which vary for each subswat, but at the moment they are set to zero. So these are the results of the validation of this calibration approach. As you can see, everything is close to zero, especially in range. I leave here the link where you can access this auxiliary data that you can eventually use to correct for these global offsets. And I also have to say that we have a technical note which summarizes this calibration validation exercise, which is prepared and should be published in the Sentinel Online library soon. So a bit of highlights in products and evolution. So one thing that we changed relatively recently, at least after last Fringe, was a correction for radio frequency interferences. Since November 2021, we have deployed the module, but just performing the detection based on our rank echoes. Since then, we have been collecting statistics on the RFI, and we have used the data on a test mode in order to tune the algorithm and assess the quality of the correction, including an assess of the impact in interferometry. And the operational filtering of the RFI has been activated and later in March 2022. Again, there is going to be a dedicated talk. Yeah, so just at the end of this section. Just one plot that I like to show that I think is not in Andrea's presentation is just to say that right now we monitor both the medication and also the residuals. So of course some of our data still contain RFIs, and this is what is tracked in the quality disclaimers I mentioned before. And here you can see a map which show where we have these residuals, which is now in a much, much smaller proportion of our slice. In particular, we know that we have some residuals when we have two SAR similar systems interference. Here we show an example of the RCM interference that we have grabbed into 2022. It's a very limited amount of data sets, but of course they are typically there because since it's a SAR signal, it's very difficult to cope with them. Then I want to go to the ETAD. So this is our extended time annotation product. This was a subject of several of the recommendations. I list them here below. So basically, we know that in order to collect this very high geometric accuracy, we need to put in place corrections. These are sometimes straightforward, sometimes not, and definitely not for all users. So the idea was to create this layer auxiliary product that would allow one to achieve this very high geometric accuracy. The processor has been deployed in the ground segment since April, and those products have been routinely generated. We are at the moment consolidating our CAVA approach and monitoring the quality of the data, correcting bugs. And the dissemination of this data, which has been producing now, should happen in the end of the year in the new data ecosystem. Yeah, so in the Sentinel Online document, you can see several documentation, including the ATBD and the product specification, and there is also a poster about the product. We have done some validation using the product, and you can see that we achieve results which are similar to our specific tool for the absolute error analysis. We currently continue the activity doing some interferometric analysis, and we are looking specifically on the provision of additional layers in order to make the solitaire correction as complete as possible. We also look to the provision of some ionospheric azimuth gradient and to try to improve the support of this product to INSAR. As we know, that we currently have some limitations due to the limited accuracy, the limited resolution of the product and the fact that we process the data for each SLC separately. We have put a pilot in place and we have had feedback from several INSAR speckle tracker users, and we are using this feedback also to continue our analysis. And we will have a session this afternoon with some dedicated talks, in particular from DLR, from JPL and DDA. And I thank you very much for the participants of the pilot who have helped us to guide our current investigations. We also do user support, as I say, and here I just want to quickly mention an analysis that we did recently of the data which was processed without pod orbiters back in 2021, because we have had some evidence from users that our initial thoughts that an analysis that this had no impact in our level 1 data was maybe not accurate. We have run analysis comparing data's processed with and without orbits, and we confirmed that at least from what we can see in the data, there is not particular degradation as we had expected. Just very, very briefly at the end, I just want to mention that we have some other activities which are not necessarily related with the MPC, but are related with some recommendations. In particular, we have now a study with the University of Leeds in order to better characterize the fading bias in the interferograms and try to do some demonstration of a method that could eventually be used to try to correct or give correction layers for this bias. I also point out you to a presentation at Wednesday by Yasser that should show a bit of what he has been doing at the moment, going to that direction. And also there was a recommendation regarding the fact that ESA should foster mechanisms to network calibration data. So I want to say that we are putting in place the CircleNet, which is precisely this. It's an initiative that should aim at giving standardized procedures for SAR calibration and for the information which is provided by different providers in terms of their calibration sites. So we have put in place now a new database. This is going to be open to the public soon, probably in October. And this should then facilitate the use of different corner reflectors, transponders, and other calibration sites by the general community. With that, I close my presentation. Thank you very much. And I call Alessandro to talk a bit more about our validation.
Thank you. Okay, thank you for having me. As a member of the SRMPC, I will discuss about the monitoring that we perform over the interferometric parameters, and I will describe recent implementations regarding the annotations of burst cycle IDs and the publication of burst ID maps. So regarding interferometric parameters, we do some routine monitoring continuously in time. Specifically, the first thing we look at is the pointing error. So we measure the Doppler centroid in time, and this is the trend of the Doppler centroid for Sentinel 1A since 2015. As we know, the Doppler centroid suffer from jumps of about 30 Hertz. This occurs when there are changes in the star tracker in the STTs. And it is something which has occurred since past years. During last years, the situation was stable. As I will discuss later, this variation in pointing can cause a decrease in the interferometric coherence. We also do perform a regular monitoring of the interferometric baseline and for the ScanSAR and TOPSAR mode, also of the burst synchronization. The way that we perform this monitoring is that we first create an OBS product, an orbit baseline and synchronization product for each acquisition, and then we pair two OBS products from two acquisitions to compute the relative baseline or the relative burst synchronization. So starting from the baseline monitoring, we compute the interferometric baseline in its three components. The way we have performed the monitoring in the past years is the monitoring of the baseline of the current cycle with respect to a reference cycle. So we have selected and we've chosen a fixed reference cycle, specifically cycle number 60 from September 2015. And for each cycle, we compute the baseline with respect to it. Recently, we have tried a different monitoring in which we, for every cycle, we compute the baseline of that cycle with respect to the previous one. So we show results from both monitoring, from both types of monitoring. Both approaches have pros and cons. In the first case, we have a fixed reference cycle, but we suffer from seasonal trends, and all the measurements depend on the chosen cycle. With the previous cycle, with the monitoring with respect to previous cycle, we capture current properties, but we always have to take in mind that the secondary cycle changes. So this is the monitoring with respect to reference cycle from 2015. You can see that at the beginning of 2015, the situation was not quite stable. But after that, the baseline, specifically the normal baseline, which is the most important one, was always under values of 250 meters. Whereas the critical baseline is at around 5 kilometers. Since about 2022, the maximum and minimum values have increased, reaching values of plus minus 500 meters, which is about 10% of the critical threshold. These were the result for the monitoring with respect to reference cycle. These are the results in the case for the monitoring with respect to previous cycle. The results are similar, so we have an increase since 2022. Moving on, we know that the interferometric performance for burst-like modes also depends on the burst synchronization. and so we perform an additional monitoring of the burst synchronization. The way this monitoring is performed is that we start from a reference cycle. We perform a direct geocoding over a grid of reference points, and then we perform an inverse geocoding from ground to the orbit of the cycle that we are monitoring. Also in this case, we perform a standard monitoring with respect to a reference cycle. It's the same cycle. And recently we have started also monitoring with respect to previous cycle. So these are the results of the burst synchronization with respect to reference cycle since 2015. We see that so it is an histogram, and the black line is the daily average. We see that there is a seasonal trend, and the average values reaches values up to -5 milliseconds of synchronization error. This is a zoom over the last 2 years. You see a significant oscillation at about September, October 2022. And it appears that the values have increased a bit after that, or at least after 2022. The average value has now reaches values at about 10 milliseconds. In order to better investigate this increase in burst synchronization error, we have implemented the monitoring with respect to previous cycle. This approach removes the seasonal trend and reduces the dispersion in the monitoring, but it also becomes more evident that since middle of 2022, there has been an increase in the synchronization error. So we've gone from 5 milliseconds to 10 milliseconds at least. One possible cause for this increase in burst synchronization error may have to do with an increase in solar activity, which has affected orbit control. We have entered into a new orbit cycle, into a new solar cycle in 2019, and it seems like it's stronger than previously estimated. Of course, to investigate this approach, this problem, we replicated a monitoring which was performed during the commissioning phase of Sentinel-1 in order to separate the instrument from the orbit control. So specifically, we analyzed the measurements from the ABS products with respect to the we compare the angles we measure from the OBS products with respect to the angles from the mission planning file. The results of this analysis is that we observe a discrepancy which has not changed in its statistical properties since the start of the mission. So from this analysis, it would appear that this increase in burst synchronization would not be caused by a deterioration in the instrument per se. Now, of course, we know that both the error in pointing and the error in burst synchronization can cause an increase in the interferometric coherence. This is a time frequency diagram for the topstar mode, and the colored band corresponds to the antenna from the acquisition from the antenna, whereas the oblique black line corresponds to the target under observation. Of course, when we create an interferogram, we have to look at two acquisitions. and we have to look at the superposition between the bands of the two acquisitions. So a point in error would cause, in this diagram, would cause a vertical shift between the two bands, which reduces the bandwidth in common and causes a decrease in the interferometric coherence. For Sentinel 1A mode IV1, we can compute that for a point in error of 30 Hertz, which would be around the worst case. For each 30 Hertz of point in error, we would have a loss of about 3% of interferometric coherence. On the other hand, a burst synchronization error would cause an horizontal shift between the two acquisitions, but we can convert this horizontal shift into a vertical one, so we can compute the equivalent point in error, and we can use the same formulas from before. This tells us that for each 5 milliseconds of burst synchronization error, we have again, for IV1 2 and 3, a loss of about 3% of coherence. It's also important to take in mind that from the way these two, the way the two shifts, vertical and horizontal one, combine, it is actually possible that these two effects can either combine together, causing a larger coherence loss, or they may compensate each other. Moving on from the monitoring, I'm here also to describe the topic of burst cycle IDs and burst ID map. So from the version 3.4 of the IPF, the annotations now contains burst cycle ID numbers in the case of TOPSAR modes. Specifically, they report two different burst ID numbers. The absolute burst ID identifies unambiguously a burst since the beginning of the mission, whereas the relative burst ID identifies it unambiguously since the beginning of the current 12-day cycle. They identify it within a subswath, whereas the burst within the same burst cycle across different subswaths will share the same burst ID. And of course, since the Sentinel 1A is synchronized, it is possible to use the burst IDs to create a unique correspondence between a burst and the area on ground that it looks at. On the topic of burst cycle IDs, returning on the topic of SAR-MPC, as the SAR-MPC website routinely publishes disclaimers whenever there is something to report. In the case of burst IDs, there is a small percentage of products which have been found to have wrong burst ID values. There is a shift by 1. And the number of affected products has been estimated on about 1 to 2%. The cause of this problem has been understood. It is related to the use of the annex time annotated in the metadata, which by design is derived from predicted orbit information, and it does not always have the required accuracy to compute the burst ID annotation. So the problem has been understood and will be addressed in the next version of the processor, which will be the 3.7 and will be delivered soon. One thing that the SAR-MPC website does, it reports the list of the affected products whenever we find products with bugs, and so the products affected by this problem are published, are reported on this website. On the last topic, so we have moved from the topic of burst ID to create the burst ID maps. The burst ID maps basically associate each are file that are maps that you can download and which contain association between each relative burst ID. Yes, and a geocoded polygon on ground. So you can download them both in SQLite format and KMZ format. They are basically databases with these fields. For each relative burst ID, the record will contain the corresponding subswot, the relative orbit number, whether it is ascending or descending orbit, the time from an X in second, and the corresponding geocoded polygon. This is an example of what you would see if you open one map in, for example, in this case in Google Earth. So this is one KMZ file for one for one orbit in a cycle, and for IV mode. So all of the red polygons are the burst footprints of that orbit, and when you open in this way, you can see for each polygon the corresponding information. This is the first version of the map. It was created using orbits from cycle number 2013 in October 2020, and it was geocoded using the WGS 84 ellipsoid with zero height, and it was validated with respect to timing annotations from cycle 2040, giving an average error within 1 kilometer. And this is the end of my presentation. So summing up, in our reports that we publish routinely, you can see all the results from this monitoring, and you can also find information on the new implementation of burst ID maps and burst IDs. Thank you.
Thank you very much. Apparently, we are pretty bad at keeping time, so we move straight away to the presentation of Andrea Recchio from ARISIS, that have been working with us on the Sentinel-1 mission since ever.
Okay. Good morning to everyone. So this presentation is about the improvement of interferometric coherence through RFI mitigation in Sentinel-1 products. Okay, it is another work that was performed in the framework of the SAR-MPC. SAR-MPC is looking at monitoring the quality of the Sentinel-1 products, but is also responsible of the maintenance of the official Sentinel-1 operational processor, the IPF. And we basically do both maintenance activities, so fixing bugs. We find bugs in the IPF, even if we are using it since 10 years. Sometimes we introduce them ourselves, so we have something to do later. And but also we work on the evolution of the operational processor, even if we know that interferometric community does not like very much evolutions, because we go to we impact on your time series. In the past, we had to go back, so from some evolution that we introduced, because we were impacting the quality of your data. And now I'm talking to you of a recent, a couple of years ago, evolution that we introduced in the in the operational processor, which is about the RFI mitigation. This is an evolution that impacts a lot on the quality of the data. It improves the quality of the data, but it could also introduce some issues for you. So our goal was really verify that these issues were not affecting the interferometric community. So RFIs are known, so they come from either from the ground or from other sensor working in the same band of Sentinel-1 and impact the quality of the data. They cause these very bright artifacts that you can see on the right. They are known since the beginning of the mission, Sentinel-1, and have increased during the mission, so we have observed an increase of the contamination. We know also that other bands are even more affected, for instance, L-band, where ALOS and also SAOCOM sensors already foresee a mitigation of the RFI in their operational processors. That's why, in the end, we decided to implement this RFI mitigation also in the Sentinel-1 processor, even considering that in the future the situation could be even worse if some services that now are outside the C-band used for Earth observation could migrate in this band, even worsening the situation. Basically, this is the algorithm that we have implemented to perform this RFI mitigation. I provide some details, but I will not go really into the more technical details. Basically, there are two steps. Pre-screening steps that is only based on noise measurements that basically is aimed at enable or not enable the RFI correction on the Sentinel-1 products. And if this pre-screening is positive, we go to the detection and mitigation module, which works on raw data, so on level 0 data, and corrects the pixel where RFIs are identified in order to remove them from the finally generated level 1 products. The most important thing is that this is a destructive step in the sense that we really need to cancel out some pixel or to filter out some bands in the spectrum in order to remove the artifacts that you have seen before. We also introduced a full new set of annotations in the Sentinel-1 products in order to describe what happened at processing level and if a product has been effectively affected by this RFI mitigation. Okay, that's it. So, starting from the RFI pre-screening, this is very important because if we had to apply the RFI mitigation to all Sentinel-1 products, the nice timelines of the product that was described before by Nuno will not be possible because the processor will take much more time to process all the Sentinel-1 products. And as a secondary point, not all the products are affected. You can see in that map that actually only the red dots were effectively needed RFI mitigation. So it's about 20% of all the products. So this way we also avoid to affect products that don't need any particular mitigation. This pre-screening is based on the so-called rank echoes that are basically all the first rank echoes at the beginning of each burst. They are signal-free, so RFIs are easily detected there because they compete with a very low thermal noise level. And then they are small, so it is easy to identify and fast to identify RFI there. If we find an RFI in one of these rank echoes, we activate the RFI mitigation for the full product. For Sentinel-1C, as described before, there will be a small evolution. We will not longer use the rank echoes because Sentinel-1C will provide dedicated noise pulses within the timeline, also within the acquisition, to perform this detection. One important point is that, of course, by doing this, we are not able to capture all the RFI events because there are some unfortunate cases where the RFI does not fall in these rank echoes but falls within the burst, and in that case, we don't activate the RFI mitigation, and we miss this RFI correction. The other case where RFI correction fails is the one mentioned before by Muriel, when the signal is so similar to SAR signal, so it comes from another SAR sensor or something like that, that we are not able to see it as an RFI. If the RFI prescreening is activated, then there is a two-steps algorithm to remove the RFIs from the data. First one is operating in the time domain. Basically, it looks for outliers in the raw data pixels. And of course, we need to compute, to look for the outliers, considering that the overall statistics of the data are varying in the raw data due to the fact that the reflectivity of the Earth, the reflectivity of the targets that are acquired will change within the data. So basically, this is a very simple statistical approach to identify all those pixels that are usually very strong and then are very likely to be RFI signals affecting our data. Once the time domain detection and mitigation has been performed, we go to the frequency domain mitigation, which is basically similar but operates in the spectrum domain of the data, and we compare the received spectrum of the data with the expected ideal spectrum, which is basically the one of the transmitted chirp. So it depends on the subsword that we are observing. A future evolution of this step could be also to use, instead of this ideal reference, the replica reconstructed by the internal calibration signals of the Sentinel-1. We look for both persistent, we call them persistent, if they appear over several lines in our data, or isolated, that appear only in isolated lines. The mitigation basically is to notching the frequencies where RFIs are detected, but at the same time in order to compensate the power in order to not affect radiometrically the products that are generated after this mitigation. Here I just provide a few examples of the effectiveness of this RFI mitigation. Basically, where you can see on the left and on the left in the second image, the original data affected by RFI. The one on the left is a ground-based RFI. The one on the right is a space-based RFI, which is, and we know this because it is very, very long. And then you can see the results of the mitigation in the quick look of the data, where basically no more very bright artifacts are observed. This is for the level 1 products, but also this gave an improvement to level 2 products that are the products derived from level 1 that, for instance, provide wind speed or RVL, so the velocity of the ocean currents. And you can see here that indeed after the mitigation, most of the artifacts that were observed in the data, in the level 2 products, have also been removed, resulting in a higher quality product. Then what I want to present to you is all the activities that we performed to ensure that this RFI mitigation step, once introduced in the data, was not affecting the interferometric quality of your data. So the idea is that the RF mitigation has two goals. Of course, remove the radiometric artifacts that affect level 1 products by correcting the raw data, but also that leave the quality of the data that are not affected by RFI the same as before. And in the next slide, I'm showing just a few examples of the analysis that we performed, in particular of this product that is shown on the right, where you can see on the top the original product and on the bottom the product after RFI mitigation. And in particular, you can see that in one of the subswords was a clear RFI mitigation that has been correctly mitigated. So basically, this is, you can see a lot of plots here. Basically, they represent the intensity of the data for all the bursts of the subsword that was affected by this RFI contamination. You can see the top plots are the co-pole channel, the bottom plots are the cross-pole channel. And then the first set of images is the intensity as it is. The second set of images is the difference between the data before and after the RFI compensation. And we can see that the difference is very reduced. It is all very greenish, the plots, except for two cases which are expected. First one, when the bursts are affected by RFI, so you can see those yellow stripes in the burst number 6, for instance, and also when the data level is very low, because in that case, also changing a very few pixels change a bit the data. But in that cases, we are changing noise, so it is not a real problem in the data quality. This is for the data intensity, and we also, okay, I was very quick. Okay. 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 We also analyzed the phase of the data, of course, by doing the self-interferogram between data before and after the RFI contamination. Now the sets of plot represented on the top is basically the interferometric coherence computed on this data before and after RFI contamination for co and cross-pole data. When is yellow, it means that interferometric coherence is 1, so the data are totally unaffected. When it is blue, the interferometric coherence is slightly decreased down to 0.95. So in any case, the interferometric coherence between the same product is still very high. And we can see again that the only effect is really observable when an RFI is present, and it's okay because we have corrected it and we have changed the interferometric coherence, and when the data are very low, so we are changing a bit the noise realization. The plots on the bottom are the scatter plot of the distribution of the pixels as a function of the data level and of the interferometric coherence. And you can see that all the yellow spots where most of the dots are located are very close to interferometric coherence of 1, meaning that the interferometric coherence is almost unaffected and the data phase is preserved. Then I just want to conclude by showing you an interferometric case study of a very strong RFI over Dubai. And basically what I will show, this area over Dubai often shows strong RFI contamination. And we basically take two Sentinel-1 products separated by 12 days and process them with and without RFI mitigation. And we use the resulting SLC products to generate two sets of interferograms and coherence maps. In particular, the interferograms were generated from products with no RFI mitigation, so the original status of the Sentinel-1 processor, and with products with RFI mitigation, so the final new status of the Sentinel-1 processor. And I will show the results of the interferometric processing in the next slides. Here is just an example of the products. So you can see that RFI contamination was really very strong. Artifacts, radiometric artifacts are really evident in the quick looks. And then after RFI mitigation, almost no radiometric artifact is observed. Now I'm going to show you the interferogram and the coherence maps of the red area, of the red box in the product, which corresponds more or less to IW1 and IW2 subswot, while IW3 was mostly C, so I discarded it basically. So this is the original interferogram with RFI mitigation not activated. Well, it's a nice interferogram, but you cannot really see the artifacts of RFI related to RFIs. But if you then go, okay, if I switch back and forth, yes, you can start to see the effect of the RFI mitigation. There are some artifacts here and there, some phase artifacts here and there that disappear if we activate this RFI mitigation. From this phase plot, it's maybe a bit difficult to see it, but if we go to the coherence map, then it starts to be very clear. So here, the artifacts in the coherence maps are clearly visible, I think, even where the RFI was present before. And then if we go to the coherence map, if we go to the coherence map when the RFI mitigation is activated, we can see that those artifacts are totally disappeared. So the RFI mitigation was effective and allowed to solve this issue and hopefully to improve the quality of some of the interferograms that you are generating around the world. Of course, maybe some of you will even did not notice any difference because you are working on areas where no RFI contamination is observed usually, but hopefully some of you noticed that this improvement that we introduced was improving the quality of your data. This is the conclusion, basically, where I summarize all what I have already said. Just a final note, this RFI mitigation is operationally applied to Sentinel-1 products since March 2022. So now it's more than 1 year that it is applied. We didn't receive complaints from the interferometric community, so hopefully this evolution was well accepted and is working well for all of you, and thank you for your attention.
Thank you very much, Andrea. Very clear, very interesting. So we have 5 minutes for questions. So is there any questions for any of the 4 presenters that no?
Are there any plans to reprocess all the old data with the correction?
No, I think that for the time being, reprocessing of the Sentinel machine is not something that we are considering. We will be looking into that with Muriel towards the end of this year. We'll try to prepare it, but it has to be submitted to the Commission, and it's really depending to cost, let's say, impact that it has. Now, it's also, so massively reprocessing the data is something that today is not in our plans. However, with this new way of accessing the data, we'll put in this data access system the Sentinel-1 processor. And this will allow all the users to reprocess a time series they believe with the latest version of the processor, such that if there is a time series that you are interested that is impacted by AFI, you will have the capacity to reprocess it by yourself.
So there's also old data from 2014, 2015, which are not really usable. So I can do by recommendation to these right now.
I think it's a very old recommendation that we have at every Fringe, and we are taking it extremely seriously. For the time being, there have been no reprocessing that was in place. We have now a precedent in the sense that Sentinel-2 is reprocessing the entire mission, so it gives us more information about how much it costs, what it means, and it was something that was absolutely not possible with the previous ground segment that we have now. With the transformation that we made over the years, going to a cloud infrastructure, this has become technically possible. It's just a matter of cost now. So we are one step further reaching that goal. Yeah.
First of all, very nice presentations, and fantastic to see that the system is working so reliably after all these years. A couple of recommendations on the last presentation for the RFI mitigation. My feeling is whenever a new satellite comes into space, we seem to start from scratch with RFI mitigation because we never decided to take the information we extract from the data about the RFI and archive them. So I would encourage the team to think about deriving parameters about the RFI bandwidth, so a time frequency behavior of RFI, and create a database that other missions can leverage so that in the future when the next C-band mission launches, you're not starting from scratch. You already have an idea what the RFI looks like. You understand what the hotspots are. So this could be a learning system that we could implement at L-band, at C-band, to document RFI, to help in mission planning, optimize the frequencies we operate in, and also use it in defense of the bandwidth. The RFI issue is growing, and having documentation about the RFI we're seeing could be useful also in defending our bandwidth.
Hi, thank you, Franz. I just want to say that I completely agree with you, and also to point out that in all these annotations that Andrea mentioned, I think we already have some useful information. So we are annotating a lot of parameters which are related to the RFIs of the data. Maybe they are not complete, maybe we have to stand, but of course any feedback on that is also welcome. And I think it would be nice indeed to then collect all this information and transform it into a more usable database. I think that we have also tried to start that at CEUS level, to try to compile and create a database at CEUS level to document this, and I think it's definitely relevant. And it's also something that we have in mind for biomass. So there, the same, we want to put in place some sort of database and hopefully try to profit from our noise acquisitions also to try to characterize this at a different band and further promote this RFI database concept.
So you'll be discussing that at the next CEO's Caval workshop, I understand. So any more questions? Time for one more question.
ICARS, there some concern about orbital tube maintenance. Do you foresee continued operations within the current orbital tube, or you plan to relax it?
So I think that the general idea is to keep the orbital tube maintenance as it is, with a caveat that we are preparing the Roselle mission, and I think that in order to prepare for we are preparing Roselle and Harmony missions, and in order to prepare these missions, we'll probably we'll have slightly to change the orbital tube strategy at some point. It was supposed to be before the end of this year. Probably it will be toward the next year. But the idea is still to keep an orbital tube very limited. It will marginally change. I'm pretty sure that you won't see any difference with respect to what it is now.
A very quick one, just for the ascending node time issue. Those products are going to be reproduced or not? The products with which have problem with the ascending node time for burst IDs?
Sorry, Harsh, I didn't understand the
Sorry,
question.
the burst
the problem
IDs.
with the burst IDs?
Yeah, some of them determining the burst ID as you guys showed today.
Sure.
Have problem because of the ascending node time in the metadata. But you guys said that it's resolved in the new version of the software.
Yeah.
I was just wondering if, similar to Falk's question for R5, but this one is easier because
I
it's
think this one you can do outside, so in this sense,
so
it's
are you guys going to reproduce at least those products affected or not?
no, we don't. This falls in the same category of the no concrete plans for reprocessing at the moment, so there is not really a plan to reprocess the product. We do know what to do, so what we could eventually do is to try to provide this information in an exterior way, so just provide a proper burst ID for the affected products, but in a quality disclaimer or something like this. But the reprocessing of the product itself or themselves is not supported at the moment.
Okay, because this one could be detected, right? We could see which one is affected. And all right. Thanks.
Yes. I mean, you have a complete list of the affected products on the quality disclaimer. So this is a big part of it. So in the end, you have this huge list of all the affected products. As Alessandro said, it's not that much. I mean, it's 2%, 1-2% of the data. But I understand that it's a problem. So of course, it's always also my wish to reprocess everything, but we have to consider the budget constraints, and
all right,
let's see.
Thank you.
I think we can close. We close the session now. Thank you very much. We are all starving. We are Muriel and myself, and we are all there in the following days. So if you have any questions coming, please do not hesitate. Thank you very much.
Thank you very much.
Thanks to you. Went smoothly.